So part 3, beginning with number 9, consider f of x equals this log. The sum I equals 1 to n, e to the x sub I. Part A, compute the gradient. Part B, compute the Hessian. Part C, show that the Hessian is positive semi-definite. Part D, prove f is convex. Part E, explain the importance in softmax regression. So convex analysis, f of x equals this log here. So we have I equals 1, n for that sum, e to the x of I. Let s equal this sum, I equals 1 to the n, e to the x of I. So, sorry about that. Just have to get this back in focus. Sorry. So here, the gradient is this partial of f with respect to x of I, and that's going to equal e to the x of I over s. So this del f equals the softmax of x, and we're going to let p sub I equal e to the x of I over s. So then from here, h sub ij equals this partial p sub I with respect to x sub j for that partial, and then equals p sub I times that quantity, sorry about that, delta sub ij minus p sub j. So h equals the diagonal of p minus p transpose. And for any vector v, v transpose hv, that equals this sum I, p sub I, v sub I squared, minus this sum I, p sub I, v sub I, that quantity squared. So this is the variance of v sub I under the probabilities p sub I. So this v transpose hv has to be greater than or equal to 0. And therefore the Hessian is positive semi-definite and f is convex, but not strictly convex. And this function is central in softmax regression because it appears in the log partition function and multi-class cross entropy loss. Okay, so moving on to number 10. Number 10, we're given the following covariance matrix here with this sigma equals first row 5, 3, 1, second row 3, 4, 2, third row 1, 2, 3. So part A, compute eigenvalues. Part B, determine the principal components. Part C, determine the proportion of variance explained by the first component. Part D, reduce the system to 2 dimensions. Part D and Part E, explain why PCA minimizes reconstruction error. So principal component analysis problem, PCA. So the characteristic polynomial, lambda cubed minus 12 lambda squared plus 33 lambda minus 21 equals 0. Eigenvalues are approximately given here. For lambda sub 1 is about 8.3485, lambda sub 2 about 2.7302, lambda sub 3 is about 0.9213. So the total variance here is that trace of sigma equals 12. So the proportion is explained by the first component, 8.3485 over 12, which is about 0.6957. So the first principal component explains about 69.6% of the variance. And approximate normalized eigenvectors, u sub 1 equals first row 0.6793, second row 0.6366, third row 0.3651. For u sub 2 is about first row negative 0.5999, second row 0.1953, third row 0.7759. U sub 3 here, first row 0.4226, second row negative 0.7461, and third row 0.5145. So a two-dimensional PCA projection keeps u sub 1, u sub 2, and w sub 2 equals this following, the u sub 1 and u sub 2 here. So the reduced coordinates are z equals this w2 transpose of x. PCA minimizes reconstruction error because the best rank k approximation to the covariance structure is obtained by keeping the top k eigenvectors. Okay, so that is number 10. Moving along now to number 11. So, let's see, sorry about that. So number 11, consider the neural network Z equals W sub 1x plus B sub 1 H equals sigma of Z, Y equals W sub 2 H plus B sub 2. Loss function L equals that 1/2 norm Y minus T squared. So here we have the following. Derive the partial derivative of L with respect to W sub 2. Derive the partial derivative of L with respect to B sub 2. Derive partial derivative of L with respect to W sub 1. And part D, state the chain rule steps explicitly. And part E, explain the vanishing gradient phenomenon. So back propagation and derivation. Partial derivative of L with respect to Y is Y minus T. And since Y equals W sub 2 H plus B sub 2, then partial derivative of L with respect to W sub 2 is a quantity Y minus T H transpose. So here we get the following. Partial derivative of L with respect to B sub 2 is Y minus T. Back propagate into H. Partial derivative of L with respect to H is W sub 2 or W2 transpose quantity Y minus T. Since H equals sigma of Z, D partial derivative of L with respect to Z equals the quantity here W2 transpose times W2 transpose Y minus T. And here element Y's multiplication with that sigma prime of Z. So partial derivative of L with respect to W sub 1 equals bracket this that W2 transpose Y minus T element Y's multiplication sigma prime of Z close bracket X transpose. And partial derivative of L with respect to B sub 1 equals that W2 transpose Y minus T element Y's multiplication sigma prime of Z. So the vanishing gradients occur when repeated multiplication by small derivatives, such as sigma prime of Z, causes gradients to shrink as they propagate backward through many layers. Okay, so that's number 11. All right, and number 12 here. So 12, consider solving AX equals B, where A equals first row 1, 1, second row 1, 1.001. Part A, compute the condition number. Part B, explain why the system is ill-conditioned. Part C, estimate perturbation amplification. Part D, explain why gradient methods may fail numerically. And Part E, explain the importance of regularization in machine learning. Okay, so an overview of this: numerical stability and matrix conditioning. Since A is symmetric, positive, definite, the two norm condition number is kappa sub 2 A equals lambda sub max over lambda sub min. Eigenvalues are approximately lambda sub max is about 2.00005. Lambda sub min is approximately 0.00004,999. Kappa sub 2 of A is about 40,002. And this happens to be very large, so the system is ill-conditioned. A small relative perturbation in B can be amplified by as much as kappa sub 2 of A equals about 40,002 in the solution. And gradient methods can be, gradient methods, may behave poorly because the level sets are highly elongated, causing zigzagging and slow convergence. And regularization improves conditioning. For example, ridge regression replaces A with A plus lambda I, which increases the smallest eigenvalue and reduces the condition number. Okay, so that is all for part 3 in the practice final exam for mathematics for machine learning. Thank you very much and have a great day.